Hello there, honors pre-calculus students. Getting down to the wire here. Let's take a look at the myriad of questions that you sent me there from section 4. Um, you've heard of top 10 lists. We go above and beyond here at Fenwick High School. I'm going to give you the top 11 most requested ones. Let's start with number 7. And strangely enough, this is an easy one. Yeah, right, Mr. Mark, whatever. All right, so we're looking for the limit as x approaches infinity of this lovely expression here, 2x plus 1 over 5x minus 1. Now again, one of the key formulas you should have picked up here from section 4. See if I can put this off to the side here quickly. The limit as x approaches infinity of 1 over x becomes 0. Okay? Well, what does that have to do with problem number 7? Instead of, well, gee, 5x minus 1, that's not a very fun denominator. What happens if we took all 4 of the individual terms and we divide by the highest degree? Okay, so in other words, here, if we take all of these and if we take the 2x and divide that by x, and the 1, divide that by x, take the 5x, divide that by x, and the negative 1, and divide that by x. What would happen? Now again, granted, that's a very unusual thing to do, but you'll notice, I've created a couple of those special terms there by doing that. And the idea is you're going to want to look at this, if at all possible, and divide everything by, say, the highest degree term that you can find, so we can create as many of those as possible. So, how about a little algebraic simplification here? 2x over x just becomes 2. The 1 over x we leave alone. 5x divided by x is 5 minus 1 over x. Now again, that's an equivalent expression to what we started with the fact that the original one there doesn't have fractions in fractions. The original expression looks better to us, but it's not useful because now we can say this is the limit as x approaches infinity of 2 plus the limit as x approaches infinity of 1 over x divided by the limit as x approaches infinity of 5 plus the limit as x approaches infinity, minus that limit as x approaches infinity of 1 over x, which, okay, take these individually. The limit as x approaches anything of a constant is going to be that constant. Again, here's our key substitution. The limit as x approaches infinity of 1 over x is 0. This is going to be a constant of 5. That's 0. So the limit as x approaches infinity of 2x plus 1 over 5x minus 1 is 2/5. All right, number 11, slightly more complicated. We're going to do this in sets, for lack of a better term here. We're still looking for the limit as t, I hate t as a variable, infinity, that was a terrible one. marginally better. Just looking at that numerator, the highest degree there is t to the third. So I'm going to take 8t to the third and divide that by t to the third. And then I'm going to add t divided by t to the third. But I'm not going to divide everything by t to the third. I'm just, again, going to take these in groups. For my denominator, the first set of parentheses, the highest degree term there is only t to the first. So I'm going to take that 2t and just divide by t minus 1 over t. And for the last group here, again, the highest degree is t squared. So that's what I'm going to divide by. So for my numerator, this becomes 8 plus 1 over t squared. For my denominator, the first term here becomes 2 minus 1 over t. I'm sorry, that's my first factor. The second factor simplifies down into 2 plus 1 over t squared. Well, that didn't simplify very much. Now again, we could go through and write this out doing the limit of this term plus the limit of that term, and then my denominators and all the rest of that. But realize here, again, it's not only these 1 over t as t approaches infinity. This becomes 0, but this term becomes 0, and that term becomes 0. So in the end, this really becomes 8 plus 0 over 2 minus 0 times 2 plus 0. How are we doing on that? 8 over 4 is 2. "17. What is the limit as x approaches infinity of cosine of x?" Wait a minute. We know the cosine graph, don't we? What? Through the magic of Desmos. Boom! Cosine x. Again, we know cosine of 0 is the maximum. Again, it's just the basic. We didn't mess around with amplitude, let alone phase shift. Thanks be to God. At 0, it's 1. At pi over 2 to the center line of 0, pi, cosine of pi is -1, cosine of 3 pi over 2, back to 0, cosine of 2 pi, back up to the maximum of 1. No matter what we do to this, it's going to keep oscillating. The periodic nature of our cosine function here, it's going to keep going back and forth between +1 and -1 to +1 to -1. There is no limit to it. It's not eventually settling down and approaching one number. It keeps going back and forth and back and forth and back and forth. There is not a single value that it approaches. The limit doesn't matter as x approaches infinity here, how close you want to try and get to infinity. This is never going to settle down. The limit does not exist. All right, for the next section, use a table of values to estimate the limit and then graph it. Okay, so if we type in square root of x squared plus 4x divided by 4x plus 1, that's a funky looking graph. But again, there's all kinds of, again, really interesting things that are happening there around 0, between 0 and say -4. Don't care about any of it. we're looking for the limit as x approaches negative infinity. So if we look at a, say, table of values, pay attention to what's happening with our f of x function here as we just, oh, I don't know, hold down our finger here. All right, let's first of all, oh, we got some zeros and some undefineds and some more zeros. Negative 1.667, negative 1.15, negative 1.6, negative 1.8, 1.9, negative 2.1, 2.2, 2.3, 2.4. And you notice every time I'm hitting the button here, that digit in the tenths place has stopped changing. It's going to be a constant too. The digit in the hundredths place appears to not be moving anymore. The thousandths place, all right, let's just hold this down and see what happens here. It's taking longer and longer for that digit in the thousandths place to change. Do you see that? I'm just holding this sucker down. We're going past negative 500 already. Negative 600. I am not going to keep holding this down till we get out to negative infinity. Okay, I'm past negative 4,000 now. Negative 0.2498 is what I've gotten it down to. I'm thinking, after holding that button down for several minutes, that this appears to be approaching approximately negative 0.2498. Well, that'll probably become a 999, which we might as well say is negative 0.25. Now they also asked for you to use a graphing device to confirm your result graphically. Well, what does that mean? Well, let's first of all get rid of the table. And now I want to put in my guess of negative 0.25. Well, again, if that's my guess, that's just going to show up as a nice line. So now it's a matter of, let's mess with the window. I want to change the window settings. I don't want to go from negative 10 to positive 10. I want to go out to say negative, where was I before? 4,000? And that y min, again, I'm guessing it's converging towards negative 1/4. So I'm going to say negative point, sorry, 0.3 as my minimum. And I'm going to say 1 as the maximum. And we'll, yeah, I mean, take a look at that. It's gotten so close that it dipped down and basically became an asymptote here. And those got so close to one another that, yes, I'm fairly confident that the negative 0.25 is the limit of that function when I take a look at the graph. Okay, so now for 21, the limit as x approaches, oh, we're going to positive infinity this time. X over the fifth divided by e to the x power. Well, isn't that interesting? However, so we got this ridiculously large number here, but then it comes back down and, oh, I guess I'm doing it backwards this time. We're supposed to look at the values here on a table. Control T. But this time we're looking at positive infinity. And notice again, they went up, but now they're coming back down. And where are we headed this time? Well, wait a minute. Those numbers are all over the place. No, realize here, I'm sorry. If you, again, take any particular value, use the right arrow to go over that, over to the next column. That's not telling you it's 61, it's 2.72037. It's not wide enough to show the whole thing. That's 2.7073 times 10 to the negative 18th power. Okay, these numbers have gotten so incredibly small. Your calculator has decided to just switch over to scientific notation. So now it's 1.54922 times 10 to the negative 39th. So yeah, from the table, from the graph, I think we can agree here that this appears to be headed towards a nice zero. Okay, then aside from the word problems, because word problems are everybody's favorite, aside from the word problems, here's where the vast majority of the questions were. If the sequence is convergent, find its limit. If it's divergent, explain why. So I guess we'll start with number 23. Now, if we did this same trick like we did before, if it is convergent, we should be able to find its limit. So we're looking for the limit as n approaches infinity of 1 plus n over n plus n squared. So now if I do that same thing that we started this video with number 7, out of those four terms, the highest degree is n squared. So if I take 1 over n squared plus n over n squared, I do this for all of them. What happens? Okay, so we get the limit as n approaches infinity of 1 over n squared plus 1 over n divided by 1 over n plus 1. So now, if I apply our new rules there for an infinite limit, the limit as n approaches infinity of 1 over n squared becomes 0. As n approaches infinity, the limit of 1 over n becomes 0. 1 over n becomes 0. Well, 1, that remains a constant 1. We got a real number. In this case, it is convergent, and the limit of it is 0. Now, don't be fooled by, oh, well, if you get a 0, then that means it, no. We're going to see one here in a moment here of one that is divergent. We wouldn't get a value, any value. We can get 0, we can get -4, we can get 57. If we get a real number with this process here of the infinite limit, then the sequence is convergent, and we should be able to find out what that limit number is. So let's take a look at 25. If we want to say the limit as n approaches the infinite. Now, can we just skip to that little trick there? So we'll take everything and we'll divide it by n squared. So n squared divided by n squared, n divided by n squared, and 1 divided by n squared. So this is the limit as n approaches infinity of 1 over 1 over n plus 1 over n squared. And apply our definitions there. The limit as n approaches infinity of the, well, the constant of 1 remains constant. 1 over n, that becomes a 0. 1 over n squared, that becomes a 0. And, oh, wait a minute, hold on. Dividing by 0? Don't do it. Don't push the calculator. No. This does not exist. This is divergent. Okay? So hopefully that makes sense here. With 23, we got a real number. This is convergent. That is the limit. Here with 25, we got an undefined value. The limit does not exist. This sequence is divergent. But wait, there's more. Let's just talk our way through this one. Don't think there's any kind of algebra that we need to do. We know, just like we talked about earlier, the cosine function. With sine, it is cyclic. It bounces back and forth. Maximum center, minimum center, maximum center. It keeps going back and forth between 0 and 1, and 0 and -1, and 0 to 1, and 0 to -1. It does not converge to any one particular number here. Although it oscillates back and forth between a predictable set of values, we're looking for one particular value where the graph reduces down and there's a nice horizontal asymptote, and that does not exist with either the sine or the cosine function. This is divergent. All right, we also had lots of problems, lots of questions with 31. I don't even know where to, okay, let's talk about where to start. Take a look, if they didn't have the brackets there, would that be less confusing? How many factors are in the numerator? If you answered 3, pat yourself on the back. Not too hard. Take it easy. Geez. Here's 1, here's 2, and again, this entire thing in the parentheses. Those are all multiplied together. Those are factors. How many factors are there in the denominator? Oh no, that was kind of a Dora moment. I just kind of like asked a question. I blinked a couple of times waiting for you guys to answer, and you didn't say anything. 3 terms in the denominator. So how about we rearrange this stuff a little bit here and say we're looking for the limit as, again, n approaches infinity, and we split this up. Let's put the constants, 3 over 2 times. Now let's split this n squared into a factor and put one in the one of the n's in the numerator and one of the n's in the denominator, and then that last factor over the other n. Oh, let's put some nice brackets around it there. So we could say this is the limit as n approaches infinity of 3/2 times, well, 1 times. Now, if I want to take this and do a little bit of algebraic voodoo here, n over n is 1. 1 over n becomes a nice little fraction there. Again, pause, rewind, think about it, you'll get there. So then this is the limit as n approaches infinity of 3/2 multiplied by the limit as n approaches infinity of 1 multiplied by the limit as n approaches infinity of 1 plus 1 over n. So if I take those individually, well, again, this is a constant. It doesn't matter what n is approaching. That remains a constant, 3/2. This remains a constant, 1. And this, okay, as we remember, 1 over n, now we do have actually a variable. As n approaches infinity, this thing becomes a 0. That becomes a 1. 3/2 times 1 times 1. Grab your calculator. And now that you know this secret, 33 is not so scary. We have, count them up, 24, n to the first, n plus 1, 2n plus 1, 4 different factors in the numerator, and oh, again, 4 factors in the denominator. So we're looking for the limit as n approaches infinity of, let's put the 24 over 6 times n over 1 of the n's, n plus 1 over 1 of the n's, and the 2n plus 1 over the final n. Do I need to write all that out? Do I need to narrate that as I write it out? So as n approaches infinity, the limit of 4 is 4. The limit of 1 is 1. And again, this becomes a 0. So 1 plus 0 becomes 1. This becomes a 0. 2 plus 0 becomes 2. So yes, it is convergent. It has a limit. That's what the limit is equal to. And of course, we couldn't go through this whole thing without doing at least one word problem. A tank has 5,000 liters of pure water. Brine, that can, oh, by the way, brine is a term that just simply means a solution that's a combination of salt and water. When you get older and you have to, for the first time, cook a Thanksgiving turkey for yourself, remember that word brine. Brine is magic when it comes to long-term roasting like that. Oh, that's the secret. Brine that has a concentration of 30 grams of salt per liter of water is pumped into the tank at a rate of 25 liters per minute. Show that the concentration of salt after T number of minutes is the following expression. Okay, so for the concentration, that's simply a ratio of the amount of salt compared to the volume of the water. So after T number of minutes, we're starting with, again, it's pure water, so there is no salt at the start. But after T number of minutes, we're going to take the concentration of the salt, which is 30 grams of salt per liter of water, And we're going to multiply that by the rate at which it's being pumped in here. So it's 25 liters per minute, so that's 25T. For the volume of the water, we're told we're starting with 5,000. And again, we're adding 25T. Again, it's being the brine is being pumped in at a rate of 25 liters per minute times the number of minutes. That'll tell us how many liters got added in. Does that make sense? I hope. All right, so a little bit of algebra here. Um, 30 times 25t over, oh, look, in our denominator we have two terms. Let's factor out, oh, I don't know, what can we take out of both of those? Say a 25. 5,000 divided by 25 would be 200, and 25t divided by 25 is just 1t, and then we can reduce this factor with that factor, so it turns out to be 30t over 200 plus t, which is, of course, the expression that they asked us to demonstrate in the first place. So what happens to this concentration as t approaches infinity? Well, we're just looking for now, part B, the limit as t approaches infinity of 30t over 200 plus t. And hopefully this looks a lot like the ones that we had before. Again, starting with number 7, with number 11. Because again, it's relatively simple here. There's only 3 terms in this expression. The highest degree is t. So let's take the limit as t approaches infinity of 30t divided by t over 200 divided by t plus t divided by t. So this becomes the limit as t approaches infinity of 30 over, sorry, I'm going to need more room here, 200 over t plus 1. And we apply our individual limits there. The limit as t approaches infinity of 30 is going to be 30. The limit as t approaches infinity of 200 over t, that becomes 0. The limit as t approaches infinity of the constant 1 will stay the constant 1. And hopefully that, in the end, that's not really that surprising. We started with something that was pure water, and then we start pumping this brine in there. We start adding this solution that has salt mixed into it. And that brine that we're pumping in has a constant concentration of 30 grams of salt per liter of water for every single liter. Well, we keep adding it, and we keep adding it, and we keep adding it after an infinite number of times. Now that 5,000 liters sounds like an awful lot to start off with here. Infinity is much bigger. So eventually, after hours and days and months and years, eventually what started off as pure water is going to become, in essence, the brine itself. The brine has a concentration of 30 grams per liter. All right, hopefully that was instructive. I'm surprised that these 11 questions didn't take me much longer than this. Hopefully that all makes sense. Good luck on that quiz.